Hello and welcome to our just about our last Zoom session for 120 Anatomy and Physiology of the Ear. Today is April 15, 2019. It's a day earlier than our usual Tuesday scheduled time for anatomy of 1:30 p.m. Central Time. And that is mainly because I will be downtown Vancouver tomorrow on Tuesday, April the 16th, doing a radio talk show on hearing loss. So basically because of that, I'm just holding this Zoom session a day early, a day late and a dollar short, a day early, just to kind of finish off the unit on eighth nerve and central auditory nervous system. I will be sending everybody, of course, an email and letting people know about this. So without any further ado, why don't we share screen and go to our notes and PowerPoint for this particular session. So here we go. If we look here at the nervous system, we covered last week the eighth nerve, building blocks of the typical nervous system, myelin, white matter, gray matter. The eighth nerve is bipolar, anatomy and physiology of the eighth nerve, how many fibers it's got. We even covered tuning curves. And we talked about pathology of the eighth nerve. And I ended last week with kind of a story, a bit of a story about, I want to make sure that I'm sharing here, because I'm not 100% sure. Okay, just want to make sure that I'm actually sharing, because I'm not 100% sure that I am. So, gotta find it. If I can make that smaller, and if I can make this maybe here. Zoom, there we are. Just want to make sure I'm sharing screen. So share screen, here we go. There we are, that's what I'm looking for. So we covered in our notes last week, starting from the top. Central nervous system, brain and spinal cord, peripheral nervous system. We talked about the pieces and parts of the typical the neuron, the building block of the nervous system. We talked about the eighth nerve being bipolar as a sensory nerve. We talked more about the physiology and anatomy of the eighth nerve, saying it was the shortest nerve, that it's tonotopic, specific fibers frequencies represented in specific places. We talked about its axons, one axon being unmyelinated between the spiral ganglia and the inner hair cells, and the myelinated axon between the spiral ganglia and the brain stem, as that it had 30,000 afferent neuron fibers servicing 3,000 inner hair cells. That's 10 fibers per hair cell. We talked about the olivocochlear bundle last week. That's the nerve running along the eighth nerve, but in the opposite direction. So have a look at the numbers here. 1,800 fibers having to serve 12,000 outer hair cells. So you can see that the innervation patterns are totally different. Then we talked about eighth nerve tuning curves last week. And then we talked about pathology of the eighth nerve last week. And I mentioned about how common eighth nerve tumors are. Not very. Only 1 in 100,000 people. 1 in 100,000 people have an eighth nerve tumor. So at any rate, where the eighth nerve goes through, the internal auditory meatus, and the tumor where it can meet at the pontomedullary junction of the brain stem. I'll show you pictures there, but you did see last week too. And just having a look there, we looked at the eighth nerve running through the internal auditory meatus. There would be the tumor, and then showing how the eighth nerve tumor had left the internal auditory meatus and now was crawling up into the brain stem area. Look at how big it is there. Okay, and we ended last week talking about an article of a woman named Linda who had an eighth nerve tumor and the surgery she went through it. And that's where we finished our Zoom session last week. So today we continue on our notes now on the top of page 3. I even showed, we talked about the term retrocochlear, that the eighth nerve is almost, pathology is almost always one ear. And that's why asymmetrical sensory neural loss, because that's what eighth nerve tumors cause, is a sensory neural loss, just like hair cell damage does, only it happens in one ear, not both. And that's why it's a red flag. If you notice an asymmetrical sensory neural hearing loss, you need to rule out, did the person have exposure to noise maybe more in one ear? If you can rule all of that out, then you need to refer to a doctor to make sure the person doesn't have a tumor, because even though it's benign, it's fatal and it will kill you. So a test done for eighth nerve tumors, we said last week, is the auditory brainstem response. So if we are looking at a picture of that, last week we looked there as well. We talked about the ABR, auditory brainstem response, something not done by the HIS, but something that is done by an audiologist. Okay, they are training at Missouri State University in Springfield on how to do this. Okay, so a normal ABR on the left and an eighth nerve tumor showing here on the right, because look at the peaks 1 to 3 interval is long. We said last week that peaks 1 to 3 represent the eighth nerves and 3 to 5 represents the brain stem. So you can look at the numbers of decibels of ear exposure, of stimulus, click stimulus exposure, and notice how the waves suddenly die out, even at 80 dB with this person of the tumor. So again, this is review. You've seen this last week, so we should perhaps continue now. I showed you that picture last week, and we read a bit about it. So now we need to look carefully more at our notes and carry on from the top of page 3. Where we are looking at the central auditory nervous system. We are now leaving the eighth nerve and moving on to the brain stem. What did we say the central nervous system is? The brain and spinal cord. All other nerves are peripheral. So the eighth nerve, even though it's a cranial nerve, is part of the peripheral nervous system. However, retrocochlear pathology includes the eighth nerve, part of the peripheral nervous system, and brain stem and or temporal lobes of the brain. Okay, so just make sure that you do know what the ABR is, the test of an eighth nerve tumor. Okay, and remember very carefully here that we talked about these things of the ABR. We said last week too, the ABR has two purposes. One, to estimate thresholds in babies. So look at here, right ear, left ear, 80 dB. It's brain waves. Have electrodes hooked up to your ears, sound being put into your ears in the form of what they call clicks, and presented at 80, 5 nice peaks, 60, the peaks begin to disappear, 40, you just have peak 5, even 20, you still see peak 5. That's good. That's for estimating thresholds, but the other one is to look at tumors. That's the other purpose of the ABR. And the right ear is normal, and the left ear may not even have much of a hearing loss. It may like be a 20 decibel, 30 decibel sensory neural hearing loss. And yet the person's ABR is completely disappearing already at 70. So tumor. Okay, now we leave the brains, the eighth nerve, and we start looking at the central auditory nervous system, CANS. Auditory areas in the brain stem and brain consist of pairs of nuclei, gray areas, or groups of neuron cell bodies linked by white tracts. Okay, remember tracts are the white myelinated axons in the central nervous system. Nerves are white myelinated axons in the peripheral nervous system. Okay, so nuclei are like ganglia, groups of cell bodies. Tracts are like nerves, white myelinated pieces of the neurons themselves. So each nucleus, each group of cell bodies in the brain stem is tonotopic. And lots of decussation, lots of crossover, back and forth crossover. So when we talk about things like that, let's get a kind of a nice grip of what we're talking about here. Let's go down a piece here. Here's what I mean. Okay, I like this picture. It's just a schematic. It's showing you a cochlea, eighth nerve, brain stem. And a brain stem is about as big as your pinky. It's as thick as your pinky. It's about the length of your baby finger. Okay? And the brain stem, if you're looking at it in reality, there's the brain stem. Here's the back of the brain stem. That's the brain. Here's the brain stem from the side. Okay? Remember, the brain stem is just the spinal cord inside your skull. If you go see my cursor waving back here, if you went lower than this, you'd be outside of the skull and going down your back. Okay? So the spinal cord inside of your brain, inside of your skull is the brain stem. And the brain stem has three parts: the medulla, the pons, the midbrain. This is not the brain stem, this is the thalamus, and this is the corpus callosum on the top. Okay? So looking here now, here's your pairs of nuclei inside that brain stem. Cochlear nucleus, that's the first auditory pit stop in the central auditory nervous system. Then you go higher up and deeper inside the brain stem is the superior olivary complexes. No, they're not green and they don't have a pimento, okay, but they're called the superior olivary complexes. You have two because there's pairs of these nuclei all the way up. And notice here how you've got arrows crossing over, and that's called decussation, crossover. So now both ears are represented by this superior olivary complex, both ears are represented by this one. And as you go higher up, you still continue to have crossover. And then another pair of nuclei. And then now you're out of the brainstem and you're in the thalamus. And we'll talk about each of these pit stops. You have 4 pit stops in the brain stem. Cochlear nuclei, superior olivary complexes, lateral lemniscus, and inferior colliculus. And we'll talk about each of them. And then MG is medial geniculate body, medial geniculate bodies, and then from there to the auditory cortex. So here's your breakdown of it. Okay? So now we'll go and look at our notes. Here's another schematic of it. Cochlea, eighth nerve, cochlear nucleus, and then to this one and to the opposite. To this one and to the opposite, crossover. Lateral lemniscus, inferior colliculus, medial geniculate bodies, and then they're showing a really small brain here. Actually, the brain should be way bigger, but it's mainly to highlight the nuclei, the pairs of nuclei, gray matter areas inside your brainstem that deal with hearing. And the very top one, Heschel's gyrus, that's actually part of the cortex of the brain. So let's look at our notes now. All right, look at our notes. The brainstem is simply the spinal cord inside the cranium, and it has 3 parts. Midbrain is the top, pons is the middle, medulla is the bottom. And again, let's look at that and make sure we have that down. This is the front of the brainstem, like facing you. And remember, this whole thing is a little over an inch long. It's the spinal cord inside your skull. The bottom part is called the medulla. The middle part is called the pons. The top part is called the midbrain. Now look where the 8th cranial nerve meets. They call it the vestibuloacoustic nerve. Remember, you got 12 pairs of cranial nerves. We only care here about the 8th, and that's this one. And notice where there. And where does it meet the brainstem? At the junction of the pons and the medulla. Oh, look, here's the 7th cranial nerve, the facial nerve. This is the 5th cranial nerve, the trigeminal nerve. It doesn't meet in the same location, does it? Okay? Now here's the back of the brainstem. The front, the back. Again, the medulla, the pons would be here, I guess, and then the midbrain would be on the top. Look at these 4 bumps. These are called the superior colliculi and the inferior colliculi. Now keep this close to your heads and hearts, because look at here, you're at the top of the brainstem. I'll once again say it. The junction of the pons and the medulla is where the 8th nerve meets. So here's the pons, there's the medulla, okay? The cochlear nuclei are at the junction of the pons and the medulla. Deeper inside the brainstem, superior olives, pons. Higher up, lateral lemniscus, still pons. Inferior colliculi, the top of the brainstem, the midbrain, and where? The midbrain, and where exactly? On the back. And look at the 4 bumps. You've got inferior colliculi are for hearing, superior colliculi are for vision. So this is right where the senses of hearing and vision first meet in the brain. Superior and inferior colliculi. Where are they located? At the top of the brainstem. What's the top of the brainstem called? The midbrain. Okay, this is just showing you the front, and that's the back. Go to our notes. Cochlear nucleus, the first area. It's a gray area. Right and left 8th nerves go to the right and left cochlear nuclei. They lie on the brainstem surface at the pontomedullary junction. They're important for making a mental image about the distance of sound. Kind of if you think of an owl in a barn, hears the rustling of a mouse under the hay. The owl is able to kind of get an idea about the direction and also the, maybe the, what do you call it, not the direction so much, but the distance. Decussation begins here. Tracts, not nerves, white matter tracts go up to ipsilateral, same side, and to opposite side, superior olivary complexes. That's called decussation. Put a star by that. Going to the next pit stop, the next pair of nuclei. Right and left superior olivary complexes receive info from the same and opposite cochlear nuclei. The superior olivary complexes, the pair of them, is the first place to receive information from both ears. So right SOC has info from both ears, and left SOC has info from both ears. All binaural interaction thus involves the superior olivary complex pair of nuclei. The SOCs are involved in 3 things. So this is a very important pair of nuclei. They are involved first with the acoustic reflexes. Think of the acoustic reflex arc. Okay, the acoustic reflex arc, the loop it takes. And we looked a little bit at this earlier in our anatomy course, and we'll look at it again here and now. I'm wondering if I even have a picture of it. I might or might not. Now, I hope I do, but I can't guarantee that we do. No, I don't have a picture of the acoustic reflex arc. I should, but I don't really here. So let's just describe it verbally so we have it. Okay, acoustic reflex loop. Sound goes in the outer ear canal, and I would jot this down on your paper while I'm gabbing away here, and I'll stop sharing for a second. Sound goes in your outer ear canal, that's pit stop 1. Middle ear, number 2. In cochlea, but what part of the cochlea? Inner hair cells, because inner hair cells send info to the brain. What's the next? 8th nerve, because the inner hair cells are mainly in cahoots with the 8th nerve. Where does the 8th nerve end? Cochlear nuclei. What happens from the cochlear nuclei? Up same side and to the opposite superior olivary complexes. Now, the superior olivary complexes give messages to the 5th cranial nerve and the 7th cranial nerve. And the 5th cranial nerve innervates the tensor tympani muscle, and the 7th cranial nerve innervates the stapedius muscle. The acoustic reflex arc. Afferent to the brainstem, efferent from brainstem back to the middle ear muscles. So you can see that the acoustic reflex covers a lot of ground. The only thing it doesn't cover is the head, the brain. But other than that, all parts of the auditory system, or lots of them, okay? And the acoustic reflex is called a reflex because it never comes up to the brain. There's no part of the brain involved. It just goes to the spinal cord inside the brain and right back out again. Just like when your hand touches a hot stove, you instantly pull back. That message never reached your head either. It went up your arm to your spinal cord, and your spinal cord sent a message straight out to your muscles to pull your hand back. Okay? So that's the first piece of the superior olivary complex role. Another part of the superior olivary complex role, share screen, is going to be directionality of sound. Another part, of the SOCs. The superior olivary complexes are highly involved in localizing the direction of sound. Okay? They compare the time of sound arrival for low frequency sounds, the intensity of sound between the ears to localize high frequency sounds. And we've covered that before too. And the third piece that the SOCs are involved in is the olivocochlear bundle, the nerve that runs counter or opposite to the direction of the eighth nerve. It goes from the brainstem to the cochlea and innervates the outer hair cells. Remember, there's 1,800 fibers only, and those 1,800 fibers have to innervate 12,000 outer hair cells. That's how the brain talks to the outer hair cells. So, and the cell bodies of the olivocochlear bundle are located at the superior olivary complexes. Weird, huh? So, 3 things that they are involved with. That's a rather important pair of nuclei. You're thinking, boy, this is getting complicated. Well, we'll have some forgiveness here. The next pit stop up, lateral lemniscus, we don't know what it does. Next, we'll go to the top one. So remember, the cochlear nuclei are at the junction of the pons and the medulla. Superior olivary complexes are located deep inside the pons. The lateral lemniscus is located higher up in the pons. And then the inferior colliculi, that pair of nuclei, is in the midbrain or the top of the brain stem. It's the largest auditory brain stem center, forms 2 mounds or bumps. The distance from the cochlear nuclei at the pontomedullary junction to the inferior colliculi is about 1 inch. They look more like 2 hills. Superior colliculi look like 2 more hills just above the inferior colliculi. So, as would be shown here. Well, sort of here, I'm looking. The back of the brainstem, okay? You're looking at the back of the brainstem. Front of the brainstem, medulla, pons, midbrain. Look at the back, there's the inferior colliculi. Superior, inferior, linking together vision and hearing. All right, we go higher up now to the medial geniculate bodies. We do not know exactly what these do either, but they are located in the auditory part of the thalamus. Now, what's the thalamus? Let's look at it in our pictures here. It's above here. Let's look at the thalamus. I'm looking. Here we go. A close-up. This is a sagittal cut, like someone cut straight down this way. And you can see the medulla, pons, midbrain, thalamus. Think of the thalamus as the grand central station of unity or union between all your senses except smell. Okay, so vision, touch, taste, hearing, okay? These senses are all together in the thalamus. And the auditory area of the thalamus is called the medial geniculate bodies. And above that is a big, thick, white tract. It's about the thickest tract in your body. It's white matter. And the purpose of the corpus callosum is to link the halves of your brain, to link the right hemisphere and the left hemispheres of your brain. Let's take a look at that once. Here's a coronal section. This is a section this way, okay? So they slice the brain this way, from ear over top of your head to ear. And you can see the gray matter on the outside, white matter on the inside. And here's the corpus callosum seen from a coronal section. This is the corpus callosum from a sagittal section. And they called it the corpus callosum. Corpus means body, callus means hard. Now, what do they mean by that? Well, in early days, and still today, if they take a brain from a cadaver and they put it in formaldehyde, which preserves the tissue material so doctors can study it, then the brain gets kind of hard or rubbery. It literally you can push it, blah, 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 okay? Whereas if you took a brain out of someone's head and put it on the table, it would kind of, all right? But if it's been pickled in formaldehyde, it stays kind of like rubbery. And anatomists would put their finger down, you have a crack, you have a fissure down the top of your brain like this, and anatomists would put their fingers down that crack and they would encounter thunk, 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 and that was the corpus callosum, the bridge, the white myelinated tract that links the right and left hemispheres of the brain. Corpus callosum. All right, just wanted to show you that. Share screen. Back to our PowerPoint. Corpus callosum. Here's another sagittal view. Medulla, pons, midbrain, thalamus, corpus callosum. And then, of course, your cortex, the wrinkly parts. And this area back here is called your cerebellum, means little brain. The cerebellum isn't involved in much thought. The cerebellum is mainly for fine motor control, threading a needle, walking finely. If you have cerebellar problems, you're staggering like you're drunk. Okay, you can still walk, but you're very, very clumsy. The cerebellum controls fine motor movements. Here's again this very valuable schematic slide. Interesting though, when you're looking at the brain, gray areas on the outside, white matter on the inside, and then we keep going up here. It's really weird. If you look at the spinal cord, it's got white matter on the outside and gray matter on the inside. And it's on the top or back of the brainstem that things invert, and that white matter becomes located toward the inside, and gray matter of the cortex now is on the outside. But just realize that in the spinal cord, the white is called tracts, and the gray is cell bodies, unmyelinated. Just thought I'd tell you. And as soon as the eighth nerve hits the brain stem, you've got a literal explosion of cells. Okay, because now you're no longer, here's a bipolar neuron fiber of the eighth nerve, which is just simply carrying a message of sound. But now you've got all these weird looking cells, some called basket cells, granule cells, octopus cells, I mean strange looking cells that deal with patterns of sound, because now things are getting more complicated up in the brain. Now, when you're getting up toward the brain itself, now you're looking at a side view of the brain, okay? And this is an important slide. This is the frontal cortex. This is the back of the brain, the occipital cortex. The frontal cortex deals with thinking, reasoning, intelligence, will to action. The parietal lobe, right where I'm circling here, deals with integration of all kinds of information, sensory, motor information. It's where stuff kind of comes together. The front is what you're going to do about it, your executive functions kind of. Here's an integration area of all kinds of information. The back of the brain is called the occipital lobe. occipital, occipital, and that deals with vision. And this here, this weird thumb, this thing here, that's the temporal lobe. And the temporal lobe deals with sound, speech, and language. So here's a side view, and this must be the left side of the brain because the front is here and the back is there. Here's a coronal view. They just split the brain. They went like this. Follow my cursor. And now you're looking at that central fissure, the crack down the top of your head. And look at these side things. Those side things are this. So if you peel that apart, if you pull that thumb away, okay, and I'll kind of even show you like this if you see my hand, okay. So this is, so how can I show that to you? The brain, you'd have to peel that thumb away, and then inside is the auditory areas. This is the church, this is the steeple. There you go. And then open up the doors and see all the people. Okay, well, with that in mind, let's go to our notes. Share, and notes. All right. Heschel's gyrus. That's the primary auditory cortex of the brain. That's where when you peel apart the temporal lobe sort of away, when you open it up, you can see Heschel's gyrus. It's called the primary auditory cortex. It's buried deep inside each temporal lobe. You need to pull apart the sylvian fissure to see it. This is the sylvian fissure. Okay? It's a cortical area, therefore it's the first area of auditory perception or conscious auditory awareness. Recall, the areas below only give reflexive response. Think of the brain very simply, okay? The brain has a complicated, a new area and an old area. So when you're looking here, there, this is the old area of the brain, the ancient area. This is the neocortex, all right? So this is the new part of the brain. This is the old part, dealing with reflexes, blood temperature, heart rate, all your fight or flight instincts, your guttural emotions, okay? And your patterns of things are done more down here where you learn how to tie shoelaces because you got used to it and you don't have to think about it anymore, okay? But your real thinking area of the brain is more the cortex, the wrinkly area. Heschel's gyrus is the primary auditory cortex, and it sends information to associative auditory areas. Auditory association areas. And this has tons of tiny, tiny little interneurons, really small neurons, because your brain has trillions of little nerves or tracts in it. Little tiny things, not big long tracts anymore, little tiny, tiny tracts that are connecting everything together. So now hearing gets connected to speech, to language, to reading, to writing. And let's see if I've got a picture that can show it even better here. This might not be a bad picture right here. Okay, now, gonna move this box out of the way. Now look at the side area of the brain. This is the right side of the brain. Frontal lobe, occipital lobe, parietal area, okay? And then temporal lobe. And see how the sylvian fissure, they pull it apart. And now you can see Heschel's gyrus. Now, what I mean to say here, this is interesting here. See this crack? This is the central sulcus. The central one. So you have the sylvian fissure, you have the big top one at the top, and you have a big crack going down here. The front half of that represents your body in terms of fingers, your mouth, your legs, your arms, muscular stuff. People with cerebral palsy have problems with this. Cerebrum, palsy, Problem is in the brain, not their muscles. Okay? Your legs represent a wee little area of this. Your mouth, huge area. Your fingertips, big area. Look at how sensitive your fingertips are. Look at how when you feel, and then the back of this behind the crack, not in front, but now behind, is the sensory area. And of the tongue, of the fingers, of the arms, of your legs, okay? And the sensory area too, for the legs is really small. For the arms is bigger. For the mouth, it's really big. For your fingertips, huge. That's why when your fingertips are so sensitive. And your tongue, when you're feeling something with your tongue in your mouth, and you might think, oh boy, that's a great big bump on my tooth, or a great big, and you look in and it's tiny. But your tongue makes it feel so big. Your mouth and your tongue represent lots of motor movement and lots of sensory information. Your fingertips, the same thing. Okay? Anyway, when you are looking at the bottom of the motors, they call this the motor strip. They call this one the sensory strip. And the bottom of the motor strip is a place called Broca's area. B-R-O-C-A, Broca's area. And Broca's area controls the motoric movement of your lips, mouth, and tongue. And what's that for? Talking. Okay? This area back here is called Wernicke's area. W-E-R-N-I-C-K-E apostrophe S. Wernicke's area. And that represents more the understanding of language. So Broca's area kind of represents the production of language. Wernicke's represents the understanding of language. Now, when people have a stroke, aphasia they call it, A-P-H-A-S-I-A, aphasia. This area might have a blood clot, or Wernicke's area might have a blood clot. And so you can have two different types of stroke. And if you're going to, let's take a look in our notes. Broca's area is one of the auditory association areas. It receives info from Heschel's gyrus. It controls motor movements of the mouth and tongue. Damage here causes disfluent aphasia, meaning the person knows what he or she wants to say, but just has trouble saying it. Wernicke's area involves meaning assigned to language. Damage here causes a fluent aphasia. The person can talk, but is losing his or her mind as to what to say. Okay? Person can speak, no problem. It's just what he or she says doesn't make any sense. I think I'd rather have Broca's aphasia than Wernicke's. This is actually a much sadder type of aphasia. The corpus callosum, the white tract that links the two hemispheres of the brain. It's the largest tract in the body. Takes about 14 years to get done. Often associated with CAPD, Central Auditory Processing Disorders. And this is problems listening. The person can hear, he just can't listen. Who has that? Children with learning disabilities, attention deficit hyperactivity disorder, learning disabilities. Audiologists call it central auditory processing disorders. Some people call it ADD, attention deficit disorders. ADHD, attention deficit hyperactivity disorders. Okay? Audiometric tests for central auditory nervous system function for CAPD and all that stuff is called central auditory testing. The HIS does not do this. The audiologist takes a whole course in this. Okay? Often this is poorly defined and often grossly overdiagnosed. More boys than girls get to be labeled with learning disabilities, but it could very well be that boys simply learn differently from girls, requiring more visual and tactile and experiential learning than girls. Beware of simplistic explanations for brain and speech, like the right side is for music and the left side is for speech. But CAPD involves difficulty with listening as opposed to actual hearing loss. And here's where we end our session. Look at it. A test called Dichotic digits. And it's done by audiologists. And dichotic means different information sent to the ears at the same time. Dichotic. D-I-C-H-O-T-I-C. Okay? Information here and information here, but different at the same time. You're trying to talk to your cousin who's driving into town and doesn't know how to find your house. So you're giving your cousin instructions over the phone. Meanwhile, your better half is going, no, that's not the way. Tell him to do all this. It's very stressful. You're listening to this ear, and you're getting competing information that's different in the other ear. Dichotic digits. Let's look at dichotic digits. Share screen. Dichotic digits test. Yikes. Now, what happens to understand the dichotic digits test? You need to know that there are two crossover areas in the brain. Eighth nerve and brain, go to the superior olivary complexes and all that stuff. You got crossover. Then you're going higher up. And then you go to the Heschel's gyrus. But there's also a crossover here. Corpus callosum. So there's two crossover areas. Okay? And another thing to note, this is incorrect. This should read left hemisphere, and this should read right hemisphere, because Heschel's gyrus is larger in the left hemisphere than it is in the right hemisphere. So there's an inaccuracy in this drawing. Okay? So make this LH and RH. Look at it this way too. The black area, outer ear canal, middle ear, eustachian tubes, cochlea, eighth nerve, brain stem, crossover. So lateral lemniscus, I call it inferior colliculus, wrong again. Cochlear nucleus, superior olivary complexes, lateral lemniscus, not drawn, inferior colliculi, medial geniculate bodies of the thalamus, and then radiating out to the right and left temporal lobes, Heschel's gyrus. But there's also a crossover happening here. So you have one crossover at the brain stem and a second crossover here. Now with dichotic digits, and here's this little fella, okay? Dichotic digits uses everything except the number 7. They use digits between 1 and 10, and they are sent in pairs simultaneous to the ear. 1, 4, for example, 9, 6, blah, blah, and the kid is asked to say, what did you hear? And he doesn't have to tell you what ear, just has to repeat the 4 digits he heard. Okay? Repeat the 4 digits he heard. In any order, doesn't matter. Dichotic digits. What happens with dichotic digits testing? There are 2 assumptions. So write these down, or look at this and put a star by it. In your notes, it's there as well. There's 2 assumptions of dichotic digits testing. Number 1. The left temporal lobe is dominant for speech. So the left in blue, you can see I drew the gray area here thicker than here to indicate that Heschel's gyrus is bigger here than on the right. So that's in most people. The left temporal lobe is dominant for speech and language. You have a Heschel's gyrus on both sides, but in most people, the left is bigger. The second assumption of dichotic digits testing is during dichotic listening, and only during dichotic digits testing, the ipsilateral same side pathways of information from the ear to the brain, or these are drawn and dotted. You have both, remember, in the brain stem, you can see this. You've got same side info and crossed over, okay? During dichotic digits testing, when you're listening to dichotic stimuli, and only when you're listening to dichotic stimuli, the ipses pathways are suppressed and the contras rule. Well, if that's the case, the right ear wins because it goes straight over to the dominant hemisphere. The left ear, the contralateral pathway goes to the non-dominant hemisphere and then has to cross it over the corpus callosum to get to the dominant left hemisphere. So winning the race, the right ear wins. More digits are remembered that were heard in the right ear. than the digits that were heard in the left ear. So the child usually is able to repeat most of the right ear digits and not as much the left ear digits. Why would that be? Because perhaps the child's corpus callosum is not done myelinating. And girls develop faster than boys. So usually in a normal person, you'll have a slight right ear advantage, maybe 52% compared to 48%. But they did experiments early on in Montreal, Canada, for people who had split brain surgery to fight seizures. And what they did was they severed this corpus callosum to reduce seizures. And it may have reduced seizures, but when they did dichotic digits testing, they had a huge right ear advantage, and very few digits to the left ear were recalled. And that gave rise to the knowledge that the corpus callosum is big time involved in dichotic listening. So again, the two assumptions: the left temporal lobe is dominant for speech, and during dichotic listening, the contralateral pathways are the only ones happening. The ipsies are suppressed, and the right ear has a shorter pathway to the dominant hemisphere. The left has a longer pathway to the dominant hemisphere. So they call that a right ear advantage. And these little kids with learning disabilities who are bouncing off of the walls tend to have a huge right ear advantage. I'll stop sharing and just nearly stop this Zoom session now, but I will say labels stick and you can't get them off. Diagnosis of learning disabilities is whoppingly overdone. Maybe the boys just learn differently from the girls. People learn in different ways, okay? Think about 40,000 years ago. The women and children sat telling stories in front of the fire, outside of the cave or inside the cave. The men were probably aimed away from the women and children with spears in their hands, doing everything but listening to the stories being told. Men are wired differently that way. Think about, and not all, I'm making generalizations, okay, because you've got guys, and then you've got guys, and then you have effeminate guys, and then you have tomboy girls, and then you have girly girls. I mean, it's a rainbow out there. There's all kinds of people, okay? We're all wired a little differently, but in general, think about the kid from the juvenile detention center that's sat in the back of the class and he's not listening and he's not learning, and now he's getting high on crystal meth or whatever, and he's at the mall and he's wearing upside down cross earrings and screw you belt buckles, and he gets picked up by the cops for whatever, ends up in juvenile detention. Finally a judge says, you're going to the army. And the kid gets a strict routine, 3 square meals a day, and he ends up becoming one of the best helicopter pilots in the world because he's good at telling where things are in space. He's smart. He's actually higher in intelligence than average, but just didn't fit in the picture and didn't color all within the lines. Okay, so I find that testing for learning disabilities often isn't always testing what it says it's testing. I find it a little overdiagnosed, but hopefully this little tutorial, this little Zoom session, I hope we enjoyed it, okay? It's just a little coverage about the, you know, the brain and brain stem and stuff like that. We just continued from the 8th nerve where we left off last week. All right, I'll stop recording now, and we'll call it a day, and I'll let you know if we have a review session or whatever for this particular 120 anatomy. I'll send an email and let you all know. Okay, I'll stop recording now.